Hi guys, I'm Coach Cowland, and in this presentation we're going to look at standing waves. So, how do instruments, woodwind instruments, and brass instruments work? Specifically, how do they make sounds of different frequencies? When a fixed length of string or an air column is caused to bounce back, a standing wave is created. When that standing wave is created, the oscillations cause air to be moved, and that makes a noise. The length of the string or the air column determines the wavelength and hence the frequency of sound that we hear. So by changing those things we can hear different frequencies. But there is a little bit more to it than that. So when we talk about standing waves, we're going to talk about nodes and antinodes. So what is a node and what is an antinode? So the points where there is a minimum deviation from the rest position are known as nodes. So on a string, the standing waves on a string making a standing wave, the nodes are these parts at the ends here where they never move from their rest position, which is the horizontal line. You can see here on this one there are actually 3 nodes. On the previous one there were only 2. So the point where there is maximum deviation from the rest position are known as antinodes. So here is the antinode for the first one, and there are 2 antinodes for the second one. So the fundamental frequency is the simplest standing wave that you can make. In a string, it would be a string that's attached at both ends, much like a guitar string, and then when it's plucked in the middle, it vibrates and creates one antinode in the middle. You can create, in addition to what's the fundamental frequency, you can also create harmonics. Here we have a second harmonic, a third harmonic, and a fourth harmonic. And in these, you can see that the original node antinode combination has been increased. So there's one more node in the middle here for the second harmonic. Here there's 2 more nodes, so there's making a total of 4. Here there's 3 more nodes making a total of 5. So each one is slightly more complicated and each one produces a slightly different frequency. That frequency is because the wavelength is changing each time, and as the wavelength changes each time, it changes in relation to the length of the string, basically as a fraction of that string length. So here we can see standing waves on a string in action, and this is the fundamental frequency, the fundamental standing wave here, and we can see the second harmonic, third harmonic, fourth harmonic, fifth and sixth harmonic, and we can look at the number of nodes that there are and the number of antinodes, and that will help us work out the wavelength of sound that we would get from each one. So in addition to standing waves on strings, we could also get standing waves in air columns, as we said. When you have an air column which is open at both ends, you end up with a situation which is very similar to the string. Now in this one, instead of having a node at each end, you have an antinode at each end. But the relationship between the wavelength and the length is exactly the same. When you have an air column that's open at one end, such as in a woodwind, you get a woodwind of the open end of the air column is a node, and the woodwind part is an antinode. So the relationship here is a little bit more complicated, a little bit different. So to find the standing wave frequency, we go back to our V equals F lambda equation, and we need to realize that lambda, the wavelength, is proportional to the length. Depending on how much of the wavelength is equal to the length will give us the frequency of the sound. V in this case is the speed of the wave on the string or in the air. Okay, thanks for watching.